So I've gotten like the third question in a row about exam stuff. So like, I'm just gonna do it all here at the beginning. So I want to take a few minutes here and talk about the exam and kind of, like what to expect and how to prepare and what we should make sure that we're focusing on. So this is just the format stuff that I talked about. I put a little bit here in about preparations. So for part one, like you'll want to know your theorems, your facts, your definitions, and really understand what these mean, like in multiple modes, whether that's like symbolic, with like variables like f of x's, graphical like a picture, tabular, what would look like in a table of values, mostly just for like ease of creating a counterexample, right? If you need to go that route. Additionally, like you'd want to know your derivative rules. Obviously, that goes without being said. But you'd want to know those like abstractly, so you could be able to do stuff like if we want to do the derivative of f of 2x times g of x to the negative 1 or something. So just like keep that in mind, that like the derivative rules matter, and they're not just like, the derivative of natural log is 1 over x or whatever, but it's, like the product quotient chain rules. Pierce, what's up?
It's kind of unrelated about how.
Okay, then let's wait on it. Okay, if it's unrelated, let's just wait on it. Okay, I don't mean to be rude, but like I just want to get through this and not hop. We have a tendency to like in this class, and I just want to try to like get through the stuff first. For part two, these are going to be like your standard homework level question. So, for example, things you should be able to do, you should be able to evaluate a limit. What are the different ways that we do that? Direct substitution, L'Hopital really become our two primary modes at this point. Could you use the stuff from chapter 1? Sure, like multiplying by a conjugate or factoring and reducing. You can still do that if that's possible for the problem. But you can use L'Hopital at any point now. We know it. We're not going to hide around being able to use it. If you can use it, you should use it. Or if you feel comfortable using it, you should use it. You should be able to compute a derivative. Again, using multiple rules, so like product, chain, quotient, in addition to the shortcuts, kind of like merged together, kind of like what we saw in test 3. You should be able to compute a derivative from an implicit formula, like x plus 2y minus xy equals 0. You should be able to find a dy dx from that. Right?
I think we do like the dy dx.
Yeah. Yep. You should be able to write the equation for a line tangent to a curve at a given point. We've done that a bunch of different ways in a bunch of different contexts, but that's like, should be able to do that still. You should be able to solve related rate story problem, for like a specific, just like one thing, like find the rate in which volume is decreasing with time or something like. Should be able to determine an absolute minimum, or I should say, or maximum, for a function on a closed interval. So like that's your, what do you do to do that? Braden?
You have to take f prime to f prime equals 0.
Mm-hmm.
And then for determining its max, you can do
Well, if it's an absolute, not local, so for an absolute, you'd need the critical numbers, not just where the derivative is equal to 0, but also potentially where the derivative fails to exist, provided that's also in that value's in the domain of f. And then you can just evaluate your critical values and the endpoints of your interval. And just the biggest one is the absolute max, and the smallest one is the absolute min. The other ones that we don't know if they're local mins or maxes just from the number. We can't tell that, but we don't care. You could also do like a first or second derivative test, but you'd have to remember to evaluate the endpoints also. I would just plug them in and just look at the numbers because it's less work for me. It's faster. Yes, Pierce.
I forgot. So when you get those points, and then you also use like your domain parameters, are you plugging those into the original?
Yes. Yes, you're plugging them into F. There you might see a proofish problem, like prove this equation has a solution on a given interval. That's just an intermediate value theorem kind of question. I might ask you to just find the critical numbers for a function here, where it's not like super duper involved. So for part 3, you'd want to look at some of the FRQs we've done before, but the ideas that are going to be centered around would be like continuity and differentiability, especially for something that's like a piecewise function, a related rates problem, an optimization problem, min-max for a function, so absolute or local, increasing, decreasing, concave up, down, inflection points for a function, should be able to do stuff like that. Does that help a little bit with some specificity for you guys on kind of like where to drill down into? And again, for the test, do you have to be a master of all of this? No, right? You can really kind of pick, you have a little bit of freedom to kind of pick the stuff that you want to do. You just have to accumulate 10 points in section 1, 15 points in section 2, 15 points in section 3. So start by doing the stuff and once you feel like you've got 15 points at least answered, go to the next section. Don't try to answer every question. You will not have time to answer every question. Lorenzo? No. So the questions in parts 2 and 3 vary from 1 point to 4 points.
So then if you get partial credit at one question, that would still... Yes,
it carries.
Okay.
It's just you're accumulating total points. So again, the more you do, the more backup you have. Braden?
Well, the questions in part 2 say how many points?
Yes, I labeled them. Pierce?
Is there some sort of way for us to know, okay, we're probably going to get 1 or 2 points from doing this problem, but even though it's out of 4, how much would get you 1 point or 2 points?
I have when I wrote the problems in my head, when I decide how many points they're worth, I have milestones in my head of what I would need to see. So if you're talking about finding the critical numbers as a question, probably have a point for doing the derivative correctly, a point for setting it equal to 0 and solving, and then a point for if there are some there, and maybe it's 2 points for the 0 and solving, depending on how difficult that solving was. If there's factoring and you had 2 different things that you had to find solutions for, and maybe it's a point for each of those sets or something. But that's what I'm doing in my head. It's just what are the major milestones to completing this problem? Can you get past milestone 1, 2, 3? That's kind of what, when I write the question, that's kind of what I'm looking for. So if you assume it's a 4-point problem, you can think to your head, what are the milestones here got to be? Well, I know I need to take a derivative. That's probably a point. So I'm going to at least do that because that's a point. Maybe I don't know what to do after that, or I know I did set the derivative, set it equal to 0 and find its domain. Well, I can do that. Maybe I don't know what to do after that, or I'm confused what to do after that, but I know I can do that. And maybe that's a point. You know what I'm saying? So that when I'm evaluating partial credits, I'm looking for milestones in progress. Talika?
Oh, I was going to ask if it's divided by chapter on the test.
No.
Okay.
It's all, everything is just mixed together.
Okay.
Because so much of this stuff
kind of
just fly, melds together. The chapter 1 stuff is just as relevant in chapter 2, 3, and 4. We're still talking about continuity. We're still talking about limits. We're still talking about differentiability. These are still constant topics.
Yeah.
And do we need all the derivative rules from test 2 when we go and talk about the stuff we do in 3 and 4? Yeah. Of course. So it's unavoidable to try to section it off. It just is one set of stuff.
Okay, that makes sense.
Beck.
Sorry, can you remind me how you test for differentiability of both these margins?
Yeah, so what you're doing is you're looking for is the derivative defined over the entire domain of your function. So you basically take the derivative and look to check if its domain matches the domain for f.
Okay.
And if it does, then it's differentiable. Where would be the places where it would fail? So discontinuity, right? Or like a sharp corner.
And you check continuity by like the left.
Yes, and you check sharp corner also with the left and right, right? Like it checks the same thing.
So you don't. Or,
The derivative from the left won't match up with the derivative from the right at that point. They'll be going to different values, which tells you there's a sharp corner there, as opposed to like a smooth corner where they're going to 0. So let's take a minute here and talk a little bit about this part 1 stuff, because a lot of people have asked about this. So let's just think about like major theorems and definitions and vocab and stuff like that that should go on to our list of things to like make sure we're familiar with, right? So you have your 3 value theorems, right? Intermediate value theorem, extreme value theorem, mean value theorem. Those would go in immediately. We have the squeeze theorem. Then we have like those are, I think that's kind of like our big sets of theorems, right? We had some little stuff like first and second derivative tests. And then like absolute min-max test. Those are a little bit more procedural, but I would still count them as like a theorem because it's guaranteeing something, right? Like if you have these conditions, then we know something, right? I mean, you could add Rolle's theorem on here, but I think we basically just use that to prove the extreme value theorem. Definitely for definition wise, you need like continuity at a point. Differentiability, well, I guess we should have the limit definition of a derivative. Yes, Lorenzo.
So the question would be like the mean value theorem, is this true or false? Or
It would be more like, say you have a function f that's continuous on this closed interval. Then, there exists some c on the open interval such that f prime of c equals, like f of b minus f of a over b minus a.
so when
And you would say to that statement, you'd say false, because you need also, in addition to continuity, you also need differentiability. So like you would say false, and you could say for this to be true, we would also need differentiability, and that would be fine. Or you could draw a picture of like something with a sharp corner where like, like here, look, this thing has, f of b minus f of a over b minus a is 0. But because there's a sharp corner, there's no place where the derivative is equal to 0, right? Like you could do that. You could draw a picture of something like that. That would work. So that's the kind of like way I would do this. So I wouldn't ask you specifically mean value theorem states blah, 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 true or false. I would have like, here's a situation that sounds like, does this meet the, sounds like the mean value theorem conclusion? Does it have everything I need in the hypothesis? And you could say like, again, you could answer if it's true, you can say true, that's just the mean value theorem. Or if I didn't have everything, or if I had like the right hypothesis but the wrong conclusion, or I was missing stuff from the hypothesis or whatever, you would say false, and then you could tell me what was missing. Or you could draw a picture of why the stuff that you're given doesn't guarantee the conclusion. Like either way of kind of going about that is okay. Does that make sense? Jacob?
So like it's
true too, or just
So if it's true, you should give some kind of justification. More often than not, it'll be like, oh, well, that's the definition of continuity. Or, oh, that's the mean value theorem. Or, like, oh, that's just like, I did the product rule with a chain rule in it, and like, here's a little bit of work that showed that. Like it won't, the truths, I'm not asking you to prove them. I'm just asking you to like explain why you know it's true. So if the explanation is just like, that's just a theorem, it's the mean value theorem guarantees that conclusion, then that's all you need to say, right? So like, that's fine. Does that feel okay?
Yeah.
Okay. And then like, let's see, we had like we have some facts like differentiability implies continuity, right? But the reverse is not true, right? Continuity doesn't imply differentiability. And your counterexample could just be anything with a sharp corner. We know the derivative doesn't exist at the corners, so you could do something like that. And then like, I think in the directions here, like, like the abstract shortcut, like if I want to do the derivative of f of 2x times g of x to the negative 1, like I might say like, oh, the derivative of this thing is equal to, and then give you something else symbolic, and it's a true or false. So like on that one, you'd probably want to just like grind through your derivative rule and just confirm, oh, it is or it isn't. You just do the problem and you'll have either you get the same thing or you don't get the same thing. And then it's like, okay, well, that was easy enough. Either way, I have my explanation or I have my counterexample. So, Carmen, you would ask kind of about this. Is this kind of what you were looking for?
Could you maybe remind me what's the extraneous value theorem?
Oh, the extreme value theorem. That was a chapter 4.1. It was in 4.1. Let's see. So it says if f is continuous on a closed interval, then we have an absolute maximum and an absolute minimum on that closed interval. So the closedness is important there, right? If you have an open interval, you do not get both the max and min guaranteed, even with continuity. And even if you had differentiability on there, you would not guarantee, both of them. Because if you have an open interval, you could have like an asymptote going on at one or both ends that would ruin an absolute minimum or absolute maximum on there. Has to be closed.
So EVT is closed intervals and the IVT is open intervals.
The IVT says, where was that at? Probably here on continuity. So again, we're continuous on a closed interval. And we have two other y values that are that sandwich some third y value. All that intermediate value theorem says, okay, well, if that's the case, then there has to be some other x on that closed interval where we can get that y value that's in between them.
Okay.
Right? So again, that needs a closed interval as well. But even if you have that one's a little bit more flexible, because if you have an open interval, you can just take a closed subinterval, and if it's true on the closed subinterval, then it'll be true on the open interval, right? The extreme value theorem, you can't quite do that. Back.
Go back over the limit definition of a derivative.
Yeah, so it just says the limit as h approaches 0 of f of x plus h minus f of x over h is equal to f prime of x, right? That's what we mean by the limit definition of a derivative. So that's just like that limit thing. Is this helpful what we're doing right now? This is kind of, I hope, what we needed, right?
You could draw graphs too.
Yeah, as a counterexample, or even like an explanation of why this has to be true. Like, like, okay, like, like I drew, here's the, here's a point A comma f of A, and here's a point B comma f of B, and I drew it continuous and differentiable. And like, oh, look, has to be a maximum or a minimum or multiple of maxes and mins. Like, I can't draw this without creating, you make an argument that way if you wanted to like verify something or provide a counterexample. You could certainly draw pictures to justify that. You might need a little bit of writing with your picture to point out to me like, what am I looking at that shows this? But like, that's certainly fine. Does that feel okay? Is that kind of what you needed to go through some of that? Okay. Yeah, no problem. And Jacob, you were asking about the same thing before classes, like how to study for this part, right? So like, again, there's 25 of them, like, so there's a lot, you only need to get 10 points out of that section. So there's lots of opportunity to like pick and choose from stuff that like, oh yeah, I know exactly what to do with this one. Like should be able to find, I would hope at least like 5 or 6 right away that you feel pretty good about, which is not bad. And then you can shotgun approach the other ones and just like, okay, there's like 5 or 10 more that I feel okay about. Like I'm gonna try to answer these other 5 or 10 and just like throw some, like just take a, like a blanketing approach to this and try to do is, if I don't feel good about a lot of them, well, I'm just going to do a lot of them and hope for the best kind of thing. But that it's very much going to be like, if you know the theorems and definitions and stuff, it should be usually pretty obvious as to what I'm getting at. And if it's not, skip it, because you don't have to do them all, right? There's 25, you only need to get 10 right for full points out of that section. And if it's me, I'm going to try to do 10 right away and then move on. And if I have time at the end, like then there's where I'm going to do some extras. Like I'm going to try to make sure I have at least, like the minimum number of points done in each section before I start doing extras. You know what I mean? And wherever I felt like the weakest, that's the place where I'm going to start doing my extras. Would be how I would approach it as a student. Like I want to try to make sure I'm not leaving points, like questions I knew how to do, because I spent a lot of time doing questions I didn't know how to do. You know what I'm saying? Does this feels helpful in terms of, okay. Do you want to do some questions from the optimization homework? We haven't really talked about that yet. I pointed that out as a likely candidate for a free response question. And again, these are not like the hardest problems in the world if you kind of have a good feel for how to approach them. But it's a story problem, so it can still be a little challenging. Let's see. So I forget what I asked you guys. Let me look here real quick. I know what block of questions I'd want to pull from. Okay. So let's grab one of these from like 25 to 31. And maybe I'm going to pick, can you go away? How do I minimize you? Yeah, let's do that. Go away. There, good. All right, let's do. Yes, Pierce.
Wait, can I ask you?
Well, I'm going to pick one
Okay.
first. Is that okay?
Yeah.
All right. Let's do like 29 or 31, I think are pretty good. Yeah. Okay. So let's just say let's do 29 for starters, and if you guys want to do another one, we can always do 31 after. So it says a right circular cylinder is inscribed in a sphere of radius r. Find the largest possible volume of such a cylinder. So close your eyes and envision what this is going to look like. When we say inscribed, what do we mean? It's contained inside. So you have a sphere with a cylinder inside of it, right? When we say inscribed, that means the cylinder is touching. So like if we have like some sphere, then like our cylinder is like doing one of those kind of things, right? Is everybody okay with how we're kind of envisioning things? And maybe that's just like, what's up?
It's a right circular cylinder.
It just means that it's like
Oh,
not tilted.
okay.
It's not like the Leaning Tower of Pisa. It's straight up and down.
That's danger of fall. That would be,
It's been leaning for a while.
yeah.
So let's go ahead and do some labeling now. It says the radius for the sphere is r. Oops. Okay. For my cylinder, we're talking about the volume of a cylinder, right? So I'm going to have a radius for my cylinder, and I need a height for my cylinder, and I have a radius for my sphere. I'm going to put some subscripts on these because I have two different radii floating around, so I really want to make sure that I have good naming conventions sorted out so I don't get confused about which radii we're talking about, right? Now notice there's no numbers involved here. Great, Mr. Kulik. The largest possible volume of my cylinder is going to be in terms of the radius of the sphere, right? So I know that the volume for my cylinder is pi r squared h, right? What I'm going to want to do now is I'm going to try to find a way to rewrite the radius of my cylinder and the height of my cylinder in terms of rs, in terms of the radius of the sphere. Okay, is everybody all right with that plan? So let's see here. I can also say that that is a radius for my sphere, right? And so that's going to be like, I need a different color. I'm going to write some yellows now. It's going to be like radius for my cylinder. It's going to be like the height of my cylinder. And let me think here for a moment. Well, I just want to it's all about drawing the right triangle. Let's see here. Let's cheat and use their picture. I'm sure they put one in here. I gave you a picture when I drew this. Perfect. Okay, so here's the trick. Let me redraw this picture a little bit neater, huh? Is that okay? I'm going to erase this and redraw real quick. It's kind of a lot going on. That's what I needed. Is everybody okay with this picture I've drawn so far? Okay. Now, this is going to be the height of my cylinder, right? So this piece here are going to be like half of the height, right? Those two pieces have to be congruent because there's no way that the center of my cylinder can't be anywhere other than the center of my sphere. If it's going to be, it has to be touching both parts, and it has to be a right cylinder. It has to be like right in the center of it. So I can say then that I'm just going to call this spot X. So we have X is equal to 1/2 height of the cylinder. And then we have X squared plus RC squared is equal to RS squared, right? So what I would do is I would solve for the RC squared. Oops. Yes, thank you. And the sneaky part was I subbed the whole squared, right? That was the sneaky part, to avoid having to do any square roots and plus or minuses and making this like just a complete pain in the buttocks. The other nice part about this is that what is RS in this situation? It's a constant, right? That's the radius of the sphere. That's going to be fixed, right? The cylinder is the thing that we're going to be like shifting the dimensions. Do we want like a short, squatty one, or do we want a tall, skinny one? Like, what do we want for the cylinder to be best sized one that we can make. So we have this. I would distribute the 2x. Why is the 2x there instead of HC? Yeah. Yeah. Good. Carmen.
Where do you get the x squared from?
Pythagorean theorem. Because I had a right triangle here in the picture.
Use like that.
Oh.
Right? Is that cool? Okay. I should have said it. I didn't. That's my fault. So let's say here that we have 2 pi x rs squared minus 2 pi x cubed. Now I'm going to take the derivative. Now the derivative is respect to, or what is the variable, I'm sorry, in this? It's a function of x, because everything else is a constant. So that first piece just turns into that. Now I'm not differentiating with respect to time, I'm differentiating with respect to x, so there's no differentials being created. Now what I want to do is I'm going to now perform a first or second derivative test. So I'm going to search for some critical values now with my first derivative, because if I'm looking for a maximum or minimum volume, that's, in this case, maximum, that's going to be where the derivative of volume is equal to 0. So I want to get the x by itself. So I'm going to subtract over that piece and then divide by 6, negative 6 pi. Yes, Pierce. Because we're differentiating, because x is the variable.
Oh.
RS is a constant.
Oh.
Let's write it this way. Hi, Elena. Sure, what's up?
Is this supposed to be -1? Or am I just supposed to use?
Yes,
Okay.
that should be -1.
Okay.
My apologies.
No, it's okay. I just didn't know if I defined it.
No, that's not in the domain of the function, so
Oh,
that would be like nothing to do there.
Yeah, okay.
Okay. No, she's doing a retake. Okay. So there's that. But that doesn't have to be my only critical value, right? Where else could I get a critical value from? Where the derivative fails to exist, right? So let's go back and look at our derivative here. What type of function is this? Braden's correct. It's a polynomial because it's a constant minus a constant times x squared. That exists everywhere. So the domain is all real numbers. I don't have to worry about that. So I found all my critical numbers now, correct? One thing I should do before I begin is I should check to make sure, am I doing this over a closed interval or an open interval? Because that'll change the technique I want to use to locate these mins and maxes. Braden? Yes, we'll get to, I was going to use the domain first, but yes. Yep. So if we go back here to the original and we look at this, the domain here What are the acceptable values of x? So they should be between 0 and the radius of the sphere, right? You definitely can't get bigger than the radius of the sphere. And if the radius of the cylinder was the same as the radius of the sphere, you'd have a cylinder with 0 height. We won't call that a cylinder. So we have an open interval that we're optimizing over. Is everybody okay with that? If you have a 0 radius cylinder, then you just have like a straight line up and down that's all height. It's not a cylinder either. So I'm going to use an open interval here, which means that I would want to do either the first or second derivative test. Is everybody cool with that plan? Okay. In this problem, what I would do is I would do a second derivative test. So we can discard the minus because it's outside of our domain. And then I'm going to do a second derivative test. So if I have the volume of, or the first derivative is this, oops, I forgot the x. We're differentiating with respect to what variable? We're differentiating x's. So that becomes 0 minus 12 pi x. And we know x is always positive. So we know that is less than 0 for all x, which means this is a maximum, and not just any maximum, because it's the only critical value, and the function is going to be concave down everywhere. It's also an absolute maximum. Everybody feels good so far? Okay. So what we need to do now, we're going to go back and we're going to take our volume formula. Oops. Lost one. And we're going to plug our x in. What's that? Braden? Thank you. So far, so good. Okay. So let's clean this up a little bit. So when I do that, I get 2rs squared over 3. And I have times 2rs over root 3. So that's going to be 4 pi rs cubed over 3 root 3. Whatever these are, units cubed. Does that feel okay? On the exam, when I give you an optimization problem, I'm going to give you the picture for you. You won't have to draw your own. And I'll even help you with, one of the parts is going to be helping you with the labeling. So I'm going to give you some names and ask you like what part of the picture should have this name based on the description. So very much kind of setting you up through the hardest part of the question, which is usually like getting it to a formula with one variable in it that I can now differentiate and do some optimization with. Does that feel okay? Pierce, what's up?
So where you have that third step, where'd you get the 3 on the 3rs squared?
I made a common denominator.
Oh.
because I was going to have to subtract those two fractions. Is that,
Yeah.
that's good? Okay. Let's do 31 here. We got a couple of minutes, right? Yeah, absolutely. All right. So same situation, except now we're asked about surface area instead of volume. So it's, you know, the same kind of picture. Here's my sphere. Here's my cylinder. And I'm going to still kind of have the same situation. Oops. So we'll do that right away for starters. And we know that x squared plus RC squared is equal to RS squared. Now we know the surface area for a cylinder is, who remembers this formula? Cylinder.
2 pi r squared.
So it's the top and bottom.
2 pi r.
The perimeter of the circle times the height of the cylinder. Well done. Now let's put some C's on all this stuff. Okay. So we're going to substitute HC for 2x. And then we're going to do RC squared is equal to RS squared minus x squared. But we also need that RC is that, right? And I'm going to drop the plus or minus because it's a length and we know it has to be positive, as Braden pointed out for us earlier. So let's start subbing this stuff in. So I have 2 pi, and then instead of r squared, I'm going to have rs minus x squared plus 2 pi, and then we'll have square root rs squared minus x squared, and then we'll have times 2x. Everybody okay so far? All right, let's try to clean this up and make the calculus maybe a little less tedious here. So we have 2 pi r squared s minus 2 pi x squared plus 4 pi x root rs squared minus x squared. I don't love looking at that product rule right here. Here's what I'm going to do. I'm going to think about that. I'm going to think about this x as the square root of x squared. If I think about that as the square root of x squared, that allows me to distribute it into the radical, and I eliminate a product rule derivative. Not that you needed to do this, but like that seems preferable to me. I just replaced the x with square root x squared. And because it's under a square root being multiplied to a square root, I can distribute it in. And that eliminates the need to do a product rule there for my derivative. Could you have still done it and just done the product rule? Yeah, but like, I'm a pass if I can get away with algebraing it.
So then how come we went from rs squared minus x squared to just rs squared times x squared?
I have, and then it's minus x to the fourth, because I distributed an x squared through,
Oh.
right?
I see.
So if I do the derivative then, that's 0 because it's constants. Then that derivative is going to be a chain rule. Oops. Does that all look okay? Okay. Oh, I don't love this. I don't love the prospect of solving this at all. This is going to be a nightmare, isn't it? Oh, yeah. That gets real bad. Well, here's the problem. So I would, let's write out what we really have here. If we set this equal to 0, we have negative 4 pi x, no big deal there. And then we'll do a little reducer-ooski there. So we have plus 2 pi, and then I have 2rs squared minus 4x cubed over square root rs squared x squared minus x to the fourth. And that is going to be dreadful, solving this. Trying to think if I have a good shortcut to apply here. Don't really think that I do. What did they do here? Let me look at this. Yeah. Yuck. So they made like a common denominator. They set the fraction equal to 0. Now they're going to have to solve something with a radical indexes in it. It just gets really gross. Let's just stop here. This is beyond the scope. The solving is getting now in the way of finishing this. So I'm going to write some terrible solving. And we get that x is equal to square root 5 minus square root 5 over 10 RS's.
We do this on the exam.
I proofread this exam 4 stinking times to make sure none of the algebra becomes too terrible like this. There's one instance where I expect you to use your calculator to do the solving, because like you just get a polynomial that there's nothing you can do with, but it's just a polynomial, and it's like pretty obvious when you see like something cubed minus something to the something x plus 7 that like equals 0. Like there's nothing you're going to do with that other than use your calculator. If you have a cubic polynomial with 3 terms in it, there's just like nothing you're going to be able to do with that other than put in your calculator and use it as a solver. So I tried very, very hard to make sure I had problems that would be, aside from that one instance, could all be done by hand, so that there isn't like any disgusting like, oh, that took me like 20 minutes to grind through the solving there, when it was like all I'm supposed to be doing is I'm doing like algebra 2 and this is supposed to be calculus right now. I tried very hard to avoid those situations, so I think I did that. Pierce.
How about the exam periods?
I think they're like the normal 80. I thought they were 80 still.
I thought they're shorter than class period. I think this faculty was
She's wrong.
think so. Well, she said they were 65, but then I think she's.
I think they might be 85.
Yeah.
Because I think that the day ends at 11. And I think it starts at the normal time.
It just says 80 on mine already. It says it ends at 10:55.
Okay, so there you go. Beck says they're 80 minutes. I'll trust that. Okay. What else? We still got what? We got like 15 or 20 minutes here, something like that. Something like that. What else? What else do you guys want to do? We got into something that this was like. This one turned into way worse than I wanted it to. I'm glad we started with 29. 29 was perfectly appropriate. Rita, what do you got?
We don't really what like a proof-ish problem.
Sure. Let me find like. So like.
I'm actually the one who found it.
So Rita, you wanted an example, maybe something like this.
Oh, yeah, it's 25.
So what I would do is my first step would be to move everything to one side. So now basically we need to show, what we want to show is there exists some C on that interval from 2 to 2 such that f of C is equal to 0. That would complete our proof, right, if we're able to show that. So Braden, this is screaming intermediate value theorem. So to use the intermediate value theorem, first thing we need to have is continuity. So how do we know that this thing is continuous? Great. Then you can just say, because it's a polynomial, that's fine, that's enough. This would not be a 4-point problem, this would probably be 2. But the polynomial state showing the continuity would be one of the 2 points. So what I would do then is, I'll call, yes, Beck.
Sorry, that's just for the proof type problem. You have to say it's a polynomial, like other problems.
To apply the intermediate value theorem, you have to have continuity,
You have to state it.
and you'd have to state why you have continuity if you're about to apply the intermediate value theorem. Okay, so now what I need to do is I need to find an x that makes this f of x negative and an x that makes this f of x positive. And if I can do that, I'm done, basically. I just apply the intermediate value theorem and it's finished. So let's see what happens when I plug the endpoints in. That's usually a good idea. So that's -8, -4, -2, -1. Well, that's less than 0. Okay, that works. If I do f of 2, well, that's 8 minus 4 plus 2 minus 1. Well, that's greater than 0. So we can say, since f of negative 2 is less than 0, which is less than f of positive 2, the intermediate value theorem states there exists a C on negative 2 to 2 such that f of C is equal to 0, and we're done. Do I care what the actual C value is? I think the C is 1 and negative 1. Actually, I think there's 2. But that's enough. Rita?
So you said like, such that like FC equals 0. Could you have done like 1? Or like, is that like what you chose?
Well, a solution is where it's equal to 0, right?
Oh, so okay. So when it's equal to 0, it's the C.
Right. Yeah. Could we have said the same thing for 1? I think so, because this is what? Negative 12, 14, negative 13. And this is 4, 6, 5. So you could say the same thing about anything less than or greater than negative 13 and less than 5. You could make the same statement about, but we don't care about those things. It's equal to 0. Elaine.
Question.
Sure.
I know I could be wrong, but for this one, I remember looking at like my last test, and there was like when I was studying earlier, and it was like a 0, and it's like for x equals 0. Doesn't x not equal 0 anywhere in this domain?
Mm-hmm.
So there's
some kind of discontinuity there,
Okay.
right?
Okay.
What are the 3 types?
Jump, movable, and infinite.
Good.
Okay.
So you'll use limits to decide which one of the 3 it is.
Oh. Okay. Okay. And then I don't know why this is like tripping me up, but like, am I finding C is like my x value?
Which one are we doing?
Number 5. I don't know why. Like I'm not processing the way to like look at that.
So C is an x.
Okay, C is an x, and then is the 1 my y? I don't know why it's like confusing.
Mm-hmm.
Okay,
It's
the
like
1
a y.
is okay. Thank you.
Sure. It's like a y, though. It's not exactly a y, right? Carmen. Yes, of course.
Thank you, by the way.
Okay. What else do you guys want to talk about?
Wait, I got a question.
Yeah. Yes, Pierce.
I don't know what, but
Did we circle back to your off-topic thing?
yeah, I was just asking how long the exam.
Oh, okay. Good.
Well, it was a little off topic, so I just
Quite a bit.
so how come if we're saying that it has a solution on this interval, we have to prove that it's less than or greater than 0? That's
So
what the IVT stated.
a solution on that interval would be an x that satisfies this, right?
Yeah.
So if I have continuity, right, if we have some y value that's less than 0, and some y value that's greater than 0, and I have continuity, somewhere along the lines it has to cross x equals 0,
Okay.
or y equals 0, and that place where it crosses will be my solution. Now, could it cross like a whole bunch of times? Yeah, but I don't care how many times it has to cross, it just has to cross at least once.
Gotcha. Thank you.
Does that feel okay? Chalika?
Can I go back?
Certainly.
Thanks.
Braden?
Oh, do you have problems like this where we use this and then we use something else to do not just a solution, but it was like 2 solutions?
Correct. Yeah. So we used, I think, the was it the extreme value theorem or something? This happened in section 4.1 or 4.2. I think we had some problems like this. Let me go back and look real quick. Yeah, so we had the other version of this problem that we did was like where instead of saying that has some solution, we had the exactly one solution version of this. So you start the same way, use the intermediate value theorem to go, okay, we got at least one, and then we do a contradiction. Okay, assume that there's more than one, and then with that you can apply the mean value theorem to generate a contradiction, is what we did. Let me go back and look at, instead of running through an entire one, let's just go back and look at this section. So that was like IVT, right? And then this was okay, and then we assume that there's a second solution, some C star, and just for without loss of generality, we'll assume that that C star is bigger than C. Doesn't matter. It's got to be on one side or the other because it's not equal to. So that tells us then that there's going to be some place where the derivative has to equal 0 in between those two, right? Because if you have like a 0 here and a 0 here, either you got to do this or you got to do that. So there's got to be some place where it's 0 in there. So if we take a look at the derivative, we see that the derivative is always positive, that setting the derivative equal to 0 has no solution to it, and that's our contradiction. So we just assume that there's more than one 0, use Rolle's theorem to say, okay, well, if that's the case, somewhere in between those two solutions, the derivative has to be 0, but this one can't be 0, and we're done. That was like the other version of this problem that you remember seeing. And they're separated by, like 2 chapters. One was a chapter 2 problem we did in like the first couple weeks of school. And the other was a chapter 4 question we did in like the last month of school. But that's the idea. Right, so if this is like, here, let's draw a picture. It'll be easier to understand. So if we have some A and B here, and okay, we found, with the IVT, we found somewhere in here, there's a C, right? And then we'll assume there's some other C star. And what we're saying here then is that like this function has to do something like that. There has to be some place where the derivative is 0 then. And okay, well, let's find that place then where it has to be 0. If we go back to our function, can't actually find that place where it's equal to 0 in between those two values. So the other option here, in this problem we saw that just that derivative is never 0, right? Could be that you get a 0, but it might be outside of the given interval. That would be okay too if I found something like, oh sure, the derivative is 0, but it's like over here. I was like, well, that doesn't matter. Still a contradiction. Is that? Sometimes the picture is like better than the symbols. It's like, oh, that's what it's saying. Yeah, that's what it's saying. So this is like, so we get that from assumption, and this is from Rolle's theorem. We get the derivative is 0 somewhere in there. What are you doing with the shoe? Whose shoe is this?
It doesn't.
Why don't you have your shoe on? I see.
It's not my fault. It's not my fault. I don't know what to say.
Carmen.
Can we go over how to write the tangent line equation?
Sure. Oops.
I do.
So let's say we have some f of x on some, so we want the tangent line for f of x at some point AB. So, well, let's just say at, let's write it this way, at x equals a. So my point that I'm going to use to write my equation for my line is going to be x comma, I'm sorry, I should say a comma f of a. That'll be my point. And my slope is going to be f prime of a. And then I just do y minus y1 equals m times x minus x1. We'll write it this way. We just fill it in. So if my f of x is, x squared minus 4 at x equals 1. So the point that I need is going to be 1 comma and then 1 squared minus 4. And then the derivative of that is 2x. So f prime of 1 is 2. So the equation for my tangent line is going to be y minus negative 3 equals 2 times x minus 1. Hello.
Hi.
How are you?
Good, how are you?
Just fine. Tessa, it's for you. Are you going home?
That's his dog.
You're welcome.
That's his dog.
Carmen, does that feel okay? Yeah, no problem. Pierce.
Are any of the like estimation problems going to be on there where it's like that like L of x?
Oh, yeah.
Oh, you mean the linearization problem? It's the same thing as writing a tangent line.
Yeah. Okay, so probably that. Yeah.
You just, if you want to make an estimate, then you like plug a value for x back into your equation for the tangent line to get your approximation. So, still just like a tangent line problem. I don't think about it as anything different. All right, who feels better about what you have to review? Good.
Really specific concepts.
Yeah.
I just need to get a 62, that's it.
Yep. But I think having it all at once will help.
Yeah.
And knowing that,
You
like,
only need 10 points or 15.
I just have to collect points. So I just have, even if I don't know exactly what to do, if I can do part of it, that's still something.
Yeah, you're
Yeah.
gonna have to give me a lot of partial credit because you're gonna see I'm gonna like try half the problem. Oh, you're just gonna stop grading after we get 15.
Correct.
Okay.
Yeah, I would not keep grading a section if you've already accumulated the necessary points. Yes. 10, 15, 15. You guys can do this.
100% all around.
My hope is that no curve is necessary.
We're going into the
Because of
I
the,
don't really know in our class, but we'll see.
you guys, you're fine. You're doing really well. Okay? This is, the tests I've written were much harder than what I did last year, based on the feedback I got from the AP about wanting to better prepare you guys for the exam. So you're getting things closer to AP exam,
Yeah.
which is much harder than what I would have written for a class.
Yeah.
Now maybe I've moved too far in that direction and probably need a little bit correction, but we'll figure that out.
Yeah.
And I don't want you guys to be discouraged because you're really, by and large, you're doing pretty well.
I mean, better than I thought I would.
And I think you know more than you've been able to demonstrate in some of these cases.
Yeah.
So.
That's something I do.